Hello, ladies and gentlemen of YouTube. Today I will show you how to solve for far-field radiated electric field um, generated by electric source J. And so let us get started. There are two ways to solve this kind of phenomena. You first of all start with your electric current and your magnetic current, and then you can integrate up until you have your magnetic and your electric vector potentials, and then you differentiate at the end here to find your resultant electric field and your magnetic fields that are radiated. So this is method number one. And then you have method number two. To do that, you again start with your distributions of your currents, and you basically integrate fully. No differentiation required. It takes a little bit of more vector identities, and you will get your radiated fields. And this is number two. So in this video I will show you method number one, which is a bit simpler. In another video maybe I show you a second method, but for today we will do integration to find potentials, and then you will differentiate in order to find your E and H. So we are trying to find magnetic vector potential, so I will write it on page here so it is clear, no confusion. Magnetic vector potential A for electric current J. Yes, okay, so what are we going to start with? Well, when we deal with electromagnetics, we usually start with the famous Maxwell's equation. So, first equation tells us that the curl of your electric field vector will be equal to the negative change with respect to time of your magnetic field vector minus your magnetic current. The second one tells us that your curl of your magnetic field intensity will be the rate of change with respect to time of your electric field intensity plus your electric current. The third one tells us divergence of D, which is your electric field intensity, will be equal to your charge density, electric charge density. There are two types, electric and magnetic. So for electric you have electric, big surprise. Divergence of magnetic field in vector equals your magnetic charge density. Okay, now we have this. Now I will show you a few relationships that will be useful for us to make things more clear and simpler, and we'll have to make some relationships. So I'll show you here J, your electric current will be equal to your electrical conductivity multiplied by your electric field vector, and then your magnetic current will be equal to your magnetic conductivity multiplied by your magnetic field intensity. Then your electric field intensity will be your permittivity multiplied by electric field vector, and your magnetic field vector will be equal to your permeability multiplied by your magnetic field intensity. So I already stated, but I will write it here again. Permittivity is going to be epsilon, and your mu will be your permeability. One has to do with electricity, one is magnetism. So this is your electrical, I guess you can say, I don't know, osmotivity through the dielectric medium, and mu is your magnetic permissivity through a magnetic medium. So how well it allows your magnetic fields to propagate in your electric fields. Now, I will show you some useful equations here, definitions. So your efficiency is going to be equal to mu over epsilon and the square root of that. And then your k is your wave number or wave vector. I always get confused, I'm not sure which one, but k is k. Equal to 2 pi over lambda, yes? So we'll write it here as omega times your square root of mu times epsilon. Then another one, I can write mu times omega k times eta, and omega times epsilon will equal k over eta. This will be useful later, so for now put it in back pocket and we will return to it. Now, going back to your Maxwell equations in time domain representation, we want to write in phasor domain. Why? Because it will be a little bit easier to work with mathematically, because we don't have to look at a bunch of differential terms. So, curl of E. What will we do in phasor domain? All you do is not very hard. You replace your ddt's with j omega. So here I'll do negative j omega, and here I'm going to put in my relationship for magnetic field vector some h minus m. This is from the first equation. Now for the second equation, we will have curl of h will equal to j omega epsilon e. So now I'm putting in the relationship for d in here, plus your j, and your divergence of E will be your charge density, electric charge density, over epsilon, and your divergence of H will be your magnetic charge density over mu. Now, what are we interested in? We are interested in electrical current source, so we will assume here that we have no magnetic currents. So our M will be equal to 0. So then, plugging that in here, we have curl of E equals to negative j omega mu times h, and then m goes away, m is 0. Here curl of h equals j omega epsilon e plus j stays the same. Divergence of E will be equal to rho E. Now it is only equal to rho E electrical charge density because we are going to assume that we are in free space in air, therefore our epsilon and our mu will be equal to 1, so we don't have to worry about it anymore. And then here, for some reason, I will go back to divergence of B, so this was a waste of time here rewriting like this. So, rho M. Now, time for some vector identities. First vector identity is, since your divergence of curl of any vector will be equal to 0. This is true. You can go look at some theories and see the derivation there, but I do not have time to show you, but you will just have to blindly believe me for now, and maybe pause video and go prove to yourself. So there is no mystery. For any A, and we know from Maxwell's equations that divergence of B is equal to 0. We know this. Yes. So, if these are both equal to 0, I can set them equal to each other, get rid of my divergence term. So now I know that my B will be equal to curl of A, arbitrary vector A. And A here is going to be our magnetic vector potential. This is how they are related to each other. The magnetic field vector is going to be the curl of your magnetic vector potential. Now, going back to this, this relationship here, I will plug it in for here. So solve for B, so mu H, and divide both sides by mu. So I will have H equal to 1 over mu curl of A. Okay, there is our first relationship that will be useful. It looks a little bit like plane wave relationship that maybe you have learned about or will learn about in future. Very useful when you're working with far field approximation. Makes your math a little bit easier. We always would like our math to be a little bit easier. Next, curl of E. So going back to first equation, I will plug in this relationship in here. So curl of E will be equal to negative j omega times your curl of your magnetic vector potential. Therefore, I will then take this to the other side, factor out your curl operator, because you can treat it as an algebraic variable or operation. So is what I will do here. So curl of E plus j omega A equal to 0. Surprise, I will give you another vector identity. Now, say we have some arbitrary scalar potential. Let's call it an electric potential. So we know that curl of the negative gradient of your scalar potential will be equal to 0. Again, I encourage you to look up this theorem on your own. I do not have time today. This will already be a long video, so bear with me. Now I'm going to go back to this. So again, these are both equal to 0, so like here I can set them equal to each other. So now I'll have e plus j omega a equals negative gradient of phi, and remember phi represents arbitrary scalar electric potential. Alright, now finally I'll just bring this over to the other side, make it nice and pretty. So E will be equal to negative gradient of phi minus j omega a. So that is our second useful equation here we will use later. Okay, now moving on to next page. We will have another vector identity. We will have a lot of vector identities in this video. It is almost too much to handle, but please be strong. Curl of any vector curl of any vector. Where am I getting curl of any vector? Well, I am going to use this second law of Maxwell's equation and put in my relationship here. So I will have j, right? I'm sorry, not j. Curl of a, plugging in here, and I'm going to multiply all sides by mu's to get rid of from the left side. So you have j omega mu epsilon e plus mu j, and the vector identity here is that this will be equal to your gradient of your divergence of a minus Laplacian operator onto a. And this identity right here is called the Lorentz condition. Very useful condition. So now what I will do is I will write here and simplify a little bit, maybe substitute, who knows, time will tell. So this gradient of your divergence of a minus Laplacian of a will be equal to j omega mu epsilon. And what is e? We know from here that e is this, so I will plug it into here. So we have j omega mu epsilon minus your gradient of phi minus j omega a plus mu j. Now, simplifying further, the gradient of divergence of a minus Laplacian squared of a will be equal to omega squared mu epsilon a. So what I'm doing is I'm distributing here j times negative 1 will be equal to 1, omega squared mu epsilon a, and then multiplying to this term I might have minus j omega mu epsilon gradient of phi plus mu j. Now, what is k? I mentioned earlier k is equal to 2 pi over lambda. What is lambda? Lambda will be c over f. You should know this. And then c will be 1 over square root of mu epsilon. This is written in many textbooks. This is very common knowledge. So what I will do is I will plug in my c into here and then simplify. So then I will have 2 pi times f times square root of mu times epsilon. So what I'm doing here is I'm using k, 2 pi, putting in this relationship for lambda, but putting in my relationship for c to get this right here. And what is 2 pi f? It is omega. So what is omega squared mu epsilon? It is the square of this. Therefore this term right here is equal to k squared. I will simplify further here. So I made a mistake here. Laplacian squared of a. So what I'm going to do is I'm going to redistribute some terms. I'm going to bring this to this side, that to this side. So I will write Laplacian squared of a plus k squared of a, bringing this here, leaving this here, equals gradient of divergence of a, bringing that to this side, to the other side, plus j omega mu epsilon gradient phi minus mu j, bringing that to that side. Here we go. Now we have this, right? and unfortunately we will have to define our divergence. And fortunately, we have the freedom to define our divergences anything we want. So let us define it in a clever way in order to cancel some things out. So what we will do is we will define our divergence as negative j omega mu epsilon phi. The reason I am doing this is because after I solve for phi here, I have 1 over j omega mu epsilon gradient of A, and this will be negative actually. Once I put that into here, you will see that these two terms will cancel out. So how will that happen? That will happen because plus n of A plus k squared A will be equal to your negative j omega mu. Oh God, I wrote it wrong. Okay. Gradient of divergence of A, and then plugging in here, so you have, you know, minus j omega mu epsilon over j omega mu epsilon. Hopefully we can see that this will be equal to 1 times your divergence of A, and it is the gradient of divergence of A. Therefore you have this minus this cancel out, minus mu j. So finally we'll have Laplacian of A plus k squared A equals negative mu j. And there you go. That is what we have. That is what we will use. And what does this look like to you? This looks like second order differential equation that we all love and seen many times. So it should not be very scary today. There we go. There is that. Now what I will do is I will take my definition for my scalar potential, I will put it back into this equation right here. So what I will have is E equals negative j mu, omega times A plus, so negative times negative cancels out, so plus gradient divergence of A, putting that in here, over j omega mu epsilon. And this will be useful in the future as well, so let's do that. Now, what will we be working on in real life? We will be working with arbitrary current distribution. So, how can we, redefine a current distribution in terms of singular source points? Well, we can just say that your arbitrary current distribution can in fact be expressed as collection of point sources. So what will we use here is called superposition. You may have heard before. We're going to take collection of all point sources and going to redefine that as our current distribution. So let us define an A generated by point source. J of R, it will be with respect to R, that is our argument, this is our vector that is controlling where we are looking or where we are interested in. So let's say we have some arbitrarily pointing vector A, and then you have your del, or your direct, components in each component of your coordinate system. So we will be working in Cartesian for now, so we have x, y, and z, and then a component of your j, of your electric. This is not a vector, this is just j, scalar. Now let us assume that A is aligned with j, means j is pointing in your A direction for your A vector. Therefore A will be equal to A hat times A sub A. Yes? So this means your A will be working upon your A direction. Therefore, we can rewrite this equation right here in terms of the A sub A. So we have del squared A sub A plus n A sub A plus k squared AA. That will be equal to negative mu. JA and your direct function of R, and that will be equal to these three components. Now, for simplicity's sake, let us assume that we are in a source-free medium when we are calculating these point sources. So we can say that your J is 0. There is no source, there is no current. Therefore, your Laplacian A plus k squared A will be 0. So, another interesting fact will be that the J, your current, vector current, if it is a point source, it will have no spatial variation. It is a single point. Why is that useful for us? It is useful because your potential will therefore be independent of theta and phi. So we will now be working in spherical coordinates, therefore we'll be using theta and phi. Therefore your A of your spherical component orientation will just be equal to AA of R, so it only will have radial dependence. Now, we want to convert our differential equation here in Cartesian coordinate systems to spherical. So, I will be right back. I will try to find you the table for converting to spherical coordinates. Okay, so now that I have my transformation parameters, guidelines here, I will show you. So this is from Appendix 7 in Balanda's textbook on Tena theory. So we will take the spherical coordinate transformation here. So we want to find our Laplacian of A, or of anything, so phi right here. So what we will have is, remember, only radial dependence, so these terms go to 0 because your differential will be 0. So then you have 1 over r squared ggr times r squared times gr of a of r. There you go, plus k squared AA, that is equal to 0. Okay, so now we have converted. We can proceed. So we've converted this into spherical representation. Now, as we proceed, let us let AA of r be equal to some function f of r over r. The reason I'm doing this is because it will make my mathematics, my differentiation a little bit easier. At the end, we will plug this back in to find our magnetic vector potential. After we solve the second order differential equation. So going on here, what will I do? I'm dropping everything. What I will do is I will substitute my f of r over r. This is r right there. F of r over r into here. So we will have 1 over r squared egr times r squared ggr of f of r over r plus k squared f of r over r, and that will be equal to 0. So I'm going to evaluate this real quick. So what do we have here? We have two functions multiplied by each other, f of r and 1 over r. So I will do chain rule. So what will we have? Let's do derivative of first times the second. So the second will be 1 over r, then gr of f of r plus, but we will actually have minus because r to the negative 1, derivative of that will be negative r to the negative second. So 1 over r squared times the original function, first function f of r. Moving on, we will have 1 over r squared egr of, redistributing this here, we will have r squared over r times egr f of r minus f of r plus k squared f of r over r, that will be equal to 0. Okay, so now we will distribute this differential term and differentiate everything. So then we will have 1 over r squared times, okay, so we will have again two functions here, r and r and f of r. So what we will do is we will have chain rule again. So first function is r, second function is ddr f of r. So we will have derivative of first function, just 1, multiplied by ddr f of r, and then plus first function r times derivative of second function d squared gr squared of f of r minus finally distributing to last term ggr f of r. Okay, plus k squared f of r over r equals 0. We see that these two cancel out here. So finally we will have, after we distribute everything, we will have 1 over r d squared gr. I'm sorry, I'm seeing here, I'm looking at notes and they're incorrect. They're wrong. So I have to correct myself, and that is why I'm pausing. So 1 over r d squared, second derivative of f of r, and plus k squared f of r over r, it will be equal to 0. So, what does this look like? Second order differential equation. We know for a second order differential equation in this form, we will have a solution of f of r will be equal to c1 e to the negative jkr times f of r I'm very sorry, my notes were correct. I am stupid today. So, never mind. What is stupid is that I did not see that multiplying both sides by r will get you cancel out your r, so you will be left with this, and that is why this form will be c1 e to the negative jkr plus c2 e to the jkr. Now, we know that our point source radiates outward, right? So we're only actually focused on wave traveling in outward direction, therefore we'll cancel this out, so we know that f of r will only be equal to c1 e to the negative jkr. And this is because c2 equals 0 for an outward radiating traveling wave by point source. Whatever. Get it. Okay. So, plugging this solution back in to, remember, a of r equals f of r over r. So we will have a of r equal to c1 e to the negative jkr over r. There we go. Now, what is the next step? Well, we will need to determine RC. Determine constant. We're not done here. We do not know what C is. We need to integrate the equation we had before, second order differential, but except now we will not have 0 on the other side. So we have JA direct R, and we have to integrate that throughout volume. Which volume? The volume surrounding JA. So, in order to do that, let us take volumetric integral, triple integral of, I'm going to factor out my AAR out of here, so I will have Laplacian plus k squared all multiplied by c1 e to negative jkr over r dv, just putting in this relationship into this equation, factoring out my this, so that will be equal to negative mu. Mu goes on the outside because it is constant. Volumetric integral of JA direct x, direct y, direct z, dv. Now, secret for you, we know that the integral over the entire solution space of a direct function will be 1. This is for a direct function. This is property of direct function. Therefore, this integral will be equal to negative mu ja, because everything will be 1. So, let us go further. We are trying to evaluate the sources, generated by point source. So what is the point source? That will be when your radial will be equal to 0. So what we actually have to do is we'll take the limit as your r vector approaches 0. Therefore you have integral from 0 to r, 0 to 2 pi for your theta, no, for your phi, and 0 to pi for your theta. Now, we have a theorem. Another theorem, real quickly for reference, this I have to show you divergence theorem. You have heard of divergence theorem, it is very, very useful. So what it tells us is, we can simplify a volumetric integral when there is a divergence of a vector. We can simplify that to surface integral by taking the surface integral of the normal components of divergence of n, f in your dot product of n. There's no divergence, no y included. So we can simplify this volumetric integral into surface integrals. So the way that we will do that is we first will actually write this out. So we will have divergence of gradient of C1 is negative jkr over r times r squared sine theta g theta g phi gr. This is your gs, gv in spherical coordinates, plus C1 k squared integral from 0 to r naught, integral from 0 to 2 pi, integral from 0 to pi, e to the negative jkr over r, and then times r squared sine theta e theta e phi dr. Okay, and the limit is your r vector approaches 0 for the entire thing. Now, what am I doing here? Well, I am just basically redistributing this into two integrals right here. So that is what is happening there. So now r naught goes to 0. Therefore, this integral vanishes. Why? Because there is an r argument here. After you simplify this, so no matter what your end result will be of your integral, you plug in r for your limit. As it approaches 0, your entire thing goes to 0, so it vanishes. We will not waste time solving all this if it will be 0 in the end. Now, back to divergence theorem. I was very excited to show you this, so I will go on. So r squared sine theta d theta d phi dr, that will be our gs, right? With an r component attached to it. R naught squared sine theta d theta d phi. And this, in this form, f is going to be equal to this because this is divergence of f. So this will be equal to f. So we will write our f here is the gradient of C1 e to negative jkr over r. And what we'll have to do is we'll have to evaluate this gradient. And what is gradient? It is just your derivative of every component. And we only have r component here, therefore we only differentiate with respect to r. So what you will have is dr r hat c1 e to the negative jkr times r to the negative first, so chain rule again. So you will have r hat times c1 e to the negative jkr, derivative of exponential, so you'll have negative jk here, and then minus c1 r to the negative second times e to the negative jkr. So what I will do is I will have r hat, I will factor out my c1, I will factor out my e to negative jkr over r, so I'll have negative jk minus 1 over r minus 1 over r e to the negative jkr over r. That is that. Now, moving on. We'll continue here. Limit as r naught approaches 0. Now we will rewrite our volumetric integral here as our surface integral through the divergence theorem simplification process. So integral from 0 to 2 pi, integral from 0 to pi of negative c1. So what we'll have is 1 plus jkr naught e to the negative jkr naught over r naught squared times spherical coordinates r naught squared sine theta d theta d phi. No more drs. Yes. So what I did here is I factored out a negative sign here, and then I factored out the r, so I have r squared now. Okay, that's how we're getting the simplification here. So going on limit 1 not approaches 0, you have integral from 0 to pi, integral from 0 to pi, negative c1 e to the negative jkr naught sine theta. So doing this first term here, distributing, we're going to separate into two integrals again. So e to the negative jkr naught sine theta d theta d phi minus jk is constant, so we pull it out of integral 0 to 2 pi, 0 to pi, r naught e to the negative jkr naught sine theta d phi. Entire limit is r approaches 0. Now, just like in the last iteration of this integral, we will have this one vanishing as well. Why? Because you have r component here, and after you integrate, you have r at the end, you plug in 0, it is 0, so we will not waste our time. So, r naught approaches 0, therefore this integral vanishes. Okay, very good. Now, for this one here, we have an exponential term, and we know that as r naught approaches 0, your exponential will evaluate to 1. Therefore, we can simplify this further, because this is our only term with an r dependence, so we can evaluate the limit here before even we evaluate the integral. So we'll say negative c1 integral from 0 to 2 pi, integral from 0 to pi, sine theta d phi. Correct? Yes, c1 goes out because it is constant. All you're left with is your what came from ds from before, so sine theta d phi. That will be equal to negative c1, 2 pi, right? No phi is here, so you have just 2 pi, and sine theta, but integral from 0 to pi of sine theta, d theta. What will that be equal to? c1, 2 pi, cosine theta from 0 to pi. Negative goes away because your integral of sine is negative cosine. What will this be equal to? Negative 4 pi c1. Now, going back, negative 4 pi c1 will be equal to, we found our we found our solution. So we evaluated this entire integral, so now we have negative 4 pi c1, so the left integral will be this. We will equate that to the right integral, which we found to be negative mu 3a. Getting a little jumbled with my words here as we get to this stage. So, get rid of negative, solve for c1, you have mu ja over 4 pi. Very good, we found our c1. Now going back to our solution for a of r, we will have mu ja e to the negative jkr over 4 pi r1 after we plug in c1. So, for arbitrarily oriented point source, we know that our magnetic vector potential will be A of your R vector, and that will be equal to mu J vector multiplied by e to negative jk r over 4 pi r. There you go. Now, we have to draw a little coordinate system here to make things a little clearer. So we'll do a Cartesian x, y, z, and say you have, we are looking for radiated fields from a certain observation point, right? So in this kind of coordinate system, you will have two vectors. Essentially, you will have your observation point here. Let's say that is the observation point. So you have two vectors. One is your r vector, and then say you have a different one, which is your source. So say your source here, observation is here. So this will be your r prime. This is your source coordinate, and therefore your source vector. Now we will have to find a vector that relates these two. So we'll actually find the projection of one onto the other. So that will be this vector here. So we will have r, big R, and that will be equal to r, your observation minus your source. Yes. So let me write here the t again so we're not confused. R prime will be your source coordinate, and your regular r will be your observation point. Okay, so now we can put this back into here so to know that for any observation point what our r will be, because it will not be source r vector. Maybe if you're looking for your radiated fields from your source point, then sure, your vector will be your source vector, but it will not be if you're at farther away point. You have to have the projection from your source vector onto your observation vector. So that is what we found here. So putting that back, we will have A of R will be equal to actually A of big R now, yes. So you will have mu J of R prime, which is your source coordinate, because the J is at the source, times e to the negative jk, and what is big R? It is R minus R hat. So observation minus source over 4 pi R minus R hat. There you go. And now, for many infinitesimal points, so remember we talked about superposition before, so say we have many infinitesimal points, i.e. a current distribution, we shall apply the famous superposition theorem. So therefore, if we have a current distribution, we can find our magnetic vector potential for that distribution as mu times your integral, your volumetric integral, so applying superposition, times j of r e to the negative jk r minus r prime over 4 pi r minus r prime with respect to dr prime. And there you go. That is your magnetic vector potential after we applied superposition, so it is valid for any arbitrary current distribution generated by source. So remember that we had a little equation here, H equal to 1, so you make the magnetic field intensity 1 over mu curl of A. So therefore, if you actually want to find your far field radiated magnetic fields, you will have H of R. And this is the differentiation step that we talked about. So we have a magnetic vector potential. Now we differentiate to find our far field radiated field. So we have H of R equal to 1 over mu curl of A of R. There's that. And remember we had another equation for E of R. And what that was I wrote it down somewhere. Yes, right here, this one. I told you we would use it again. So we have E of R equal to negative j omega A of R plus gradient of divergence of A of R over j omega mu epsilon. So that is the differentiation portion for your electric radiated far-field electric fields. So if you don't want to do all of this, you can actually do the equivalent equation. So using Maxwell's, so equivalent you are using Maxwell's equation will be your second law here. So what you will do is you have your you know that your curl of H will be j omega epsilon E, yes. Therefore your E of R will be 1 over j omega epsilon times your curl of H. So if you've already found this, you can do a relationship to find your E of R instead of doing all of this work. This is an alternative method for finding E. So yes, there you go. There is your magnetic vector potential. Now, real quick, before you go, I'm going to show you how to just equate this to your electric vector potential. So what we will use is, you can go back to the beginning, same process, except you're instead starting with, first Maxwell's equation, and then going through everything. You're just doing it with respect to a different, starting point to find your electric. But what we can use actually is called duality theorem. So duality theorem is that people have done this. People have done all the work and they've proved it. So now, for us, we have visualized. You cannot spend all this time doing this, so we just use duality theorem. For that, you have A's will convert to F's, so magnetic to electric, potential. Your electric fields will convert to your magnetic fields. Your J's will become M's. And the curveball here, your H's will become negative E's due to the orthogonal relationship of the two for a traveling TEM wave. Permeability goes to permittivity. So, if you actually want to find electric vector potential for M, magnetic current source, you will just replace everything you see in here with duality variables. So you will have F equal to epsilon times your volumetric integral of M, magnetic current source, E negative jk r minus r prime over 4 pi r minus r prime times gr prime. So there you go, same form as your magnetic vector potential. Now it's electric, but it is due to magnetic current sources. So therefore, E of R, magnetic, magnetic R, negative 1 over epsilon, curl of F. So once you have your electric potential, you solve for your magnetic, or electric field induced by magnetic current source. And then you have H, magnetically induced of R, equals negative j omega F of R plus gradient divergence of F of R over j omega mu epsilon. And just how I showed you in the alternative form to find, instead of doing all of these operations, once you have your E, you can find your H through Maxwell's relationship that H will be equal to negative 1 over j omega mu times your curl of E of R. This is once again alternative method. Okay, one last thing before we go. We want to find total fields. Maybe sometimes you will not have only electric currents, you might have magnetic currents as well. So what do? You take your magnetic current induced fields, you take your electric current induced fields, and you just add them together. So total fields due to magnetic and electric current sources, E totally will be E induced by electric sources, current sources, plus E induced by magnetic current sources will be negative j omega A plus gradient of divergence of A over j omega mu epsilon minus that 1 over epsilon Q of F. And then your total magnetic fields will be the summation of the magnetic fields induced by electric and magnetic currents. So you will have 1 over mu curl of A minus j omega F plus gradient of divergence of F over j omega mu epsilon. So yes, there you go, there are your total fields. If you have made it to the end of this video, I congratulate you. Now you are a few IQ points smarter, and you can show off to your friends. Now you can show, I know how to solve for radiated fields due to electric or magnetic current sources. It doesn't matter which one you show me, I solve for everything. So yes, thank you for watching, everyone. In another video I will show you the second method here, direct integration. It's not necessarily more work, it's just a little bit more difficult. Got to keep more track of things, use some more vector identities. But in terms of lengths and steps, it is, in my opinion, a little bit shorter, just a little more complicated. So we will have fun in that video. Again, thank you for watching, and please like, subscribe, leave me a message what you thought about the video, how I can improve, and I will see you next one. Have a good day.